When Dmitry Mendeleev first organized the elements, he looked past simple atomic weights to identify patterns in chemical behavior, allowing him to predict elements that had not yet been discovered. One of the most reliable patterns in the table is first ionization energy, the precise amount of energy required to strip the most loosely bound electron from a neutral atom in the gas phase. Moving from left to right across a period, the atomic number increases, adding more protons to the nucleus. This graph shows theoretical ionization energy for period 2. Adding protons creates stronger attractive force, meaning the energy required to remove electrons follows a perfectly linear upward trajectory. This trend is the foundation of introductory chemistry. A positive nucleus creates a tighter grip. Relying strictly on atomic number creates a sense of flawless, linear predictability that suggests nature scales in simple, manageable steps. Experimental reality tells a different story. When we measure the actual ionization energies for period 2, the line becomes jagged, showing a sharp drop between nitrogen and oxygen. This textbook problem identifies the quebra inesperada, the unexpected drop, that occurs when moving from nitrogen at atomic number 7 to oxygen at atomic number 8. The data shows nitrogen requires 1402 kilojoules per mole to lose an electron, while oxygen requires only 1314. Oxygen has 8 protons, nitrogen only has 7. Under the laws of basic electrostatics, oxygen should hold its electrons tighter, yet it is significantly easier to ionize. To understand this, we have to look past the raw atomic number and calculate the net force actually felt by the outer electrons. These empirical anomalies identify the specific coordinates where basic electrostatics stop working and the deeper physical laws emerge. In a multi-electron atom, valence electrons do not feel the full pull of the nucleus. Inner shell electrons repel them, acting to buffer the positive charge. We calculate this as the effective nuclear charge, atomic number Z, minus screening constant S. The standard method for finding the screening constant is Slater's rules, turning a complex quantum environment into algebraic approximations. Under these, electrons in the same shell contribute a shielding value of 0.35, while those below shield much more effectively at 0.85. These rules assume that electron clouds are essentially spherical, average distributions of charge. If this shielding model holds up, calculating the effective nuclear charge should provide the reason for oxygen's lower ionization energy. For nitrogen, the math yields a screening constant of 3.1, leaving an effective nuclear charge of 3.9. For oxygen, the additional valence electron increases the constant to 3.45. Subtracting that from its 8 protons gives an effective nuclear charge of 4.55. Oxygen's valence electrons feel a net positive charge of 4.55, much higher than nitrogen's 3.9. The nucleus in oxygen is exerting a stronger pull. According to the math, oxygen should require more energy to ionize, but the empirical data proves that it requires less. The spherical average model used in Slater's rules lacks the resolution to account for this anomaly. To find the truth, we must move beyond simple algebra and into the dynamic geometry of quantum waves. Electrons are not points of charge orbiting a nucleus. They are three-dimensional standing waves of probability. Mapping their true location precisely requires solving the complex Schrödinger equation. These wave equations move from simple one-dimensional space into complex three-dimensional spherical coordinates. The resulting radial probability functions show that electrons occupy specific spatial distributions rather than a smeared average. Because these geometries are distinct, electron interactions depend strictly on their specific quantum address. Nitrogen's valence architecture consists of 3 electrons in the 2p subshell. Under Hund's rule, electrons occupy separate orbitals singly before they begin pairing. Nitrogen places 1 electron in each of the 3p orbitals. By occupying separate axes, x, y, and z, these electrons remain spatially distant, minimizing their mutual repulsion. Oxygen has 4 p electrons, but only 3 available orbitals. To accommodate the 4th electron, oxygen is forced to pair 2 electrons into a single orbital, making them share the exact same spatial wave function. Compressing 2 negative charges into the same confined spatial volume creates intense, localized electrostatic repulsion. This repulsion, the pairing penalty, destabilizes the electron. The localized repulsive force between these two paired electrons outweighs the increased pull from the nucleus, making the paired electron significantly easier to eject. The periodic table serves as a macroscopic reflection of quantum spatial architecture and the physical pressures of electron repulsion.